Hello everyone, this is our video example 2 that corresponds to our lecture where we talked about vapor-liquid equilibrium, but in this case with only a single condensable component. This question is actually not from the textbook. The question is actually posted online, so print out the handout and follow along here as we go through this example. So in this example, we have pure chlorobenzene in a flask, and it's attached to an open-end mercury manometer. When the flask contents are at a particular temperature, 58.3 degrees C, we are given the heights of the manometer arms on both sides. And then at 110 degrees C, we are given the arms again at different heights. So we're also given atmospheric pressure is 755 millimeters of mercury. In part A, we are just asked to find the constants in our Clausius-Clapeyron equation, our latent heat of vaporization, and this equation constant B. And part B actually requires us to solve the material balance problems, where now the air that is saturated with chlorobenzene at a particular temperature and pressure, we're going to cool that down in this condenser to 58.3 degrees C. So some of the chlorobenzene is going to condense, and we want to estimate the percentage of this chlorobenzene that is condensed in that stream. So let's start with A, where we're looking at pretty much a review of manometers. And to try to understand the heights in those arms, let's draw a diagram to help us understand this. Here is our manometer setup. On one end, we have our chlorobenzene, so it's connected to this flask. And on the other end, this is an open-end mercury manometer, which means that it is open to atmosphere. So what happens on the left arm is some of the chlorobenzene at different temperatures will vaporize, and that vapor is going to exert pressure, so that's our pure component vapor pressure P star at a particular temperature. On the other side, it's open to atmosphere, so now you have atmospheric pressure on one end, and then you have your vapor pressure on the other end, and that's going to cause a difference in the heights in the manometer arms. So what this is saying is that at the temperature of 58.3 degrees C, we have H1, which is the arm that is attached to the flask, is 744 millimeters. That's our H1. And H2 on the other side is 52 millimeters. At a higher temperature, 110 degrees C, what you expect is more chlorobenzene to vaporize. So you're going to have a higher P star. Since you have more in the vapor phase, it's going to exert a higher P star. So what happens is it's going to push the H1 down, and it's going to push H2 up, and that's why you see H1 now drops to 577 millimeters, and then H2 is 222 millimeters. All right, so how do we use these values to figure out our P star? Let's review our manometer principles. The concept of manometers is that any two horizontal points within the same continuous fluid is at the same pressure. So in this case, we're going to look at pressure at point X and pressure at point Y on the two arms, because both of them are on the point within the mercury, which is a connected fluid right there. So what is the pressure at point X? The pressure at point X is P star. So you have your vapor pressure that's exerting down on point X, plus the fact that you have this height of mercury that is exerted on point X, and that height is H1 minus H2. So for the pressure at point X, you have your P star plus H1 minus H2. On the right-hand side, all you have is your P atmosphere. Now what you see down here is that in terms of my pressure, all I did was just took the heights and subtracted one from the other, because we're going to do this entire problem in head of fluid, in this case head of mercury. So this is in millimeters of mercury. So hopefully here you see the power of using head of fluid to do pressures. When you're doing everything in terms of a particular head of fluid, the math turns out to be a lot simpler because you're just adding and subtracting heights in this case. If you're a little unsure about what this idea of head of fluid is and how manometer works, please go back to chapter 3 when we talk about process variables, and we looked at manometers when we talk about pressure, to give yourself some review on these concepts right here. So now we can rearrange this equation to get our P star, and we can put in our two conditions to get to solve for our P star. So at 58.3 degrees C, we put in all the values for PATM that we are given, the two heights that we are given. At 58.3 degrees C, we see that the vapor pressure of our chlorobenzene is 60 millimeters of mercury. At 110 degrees C, it goes up to 400 millimeters of mercury. Now we have these two conditions. So we have two values of P star at two different temperatures. The Clausius-Clapeyron equation has two unknowns: our delta HV, latent heat of vaporization, and our integration constant. So two equations, two unknowns, we can solve for those two unknowns. Here's the Clausius-Clapeyron equation again. It's an equation that relates our pure component vapor pressure with our temperature and how it changes with temperature. And we have the two constants in there. So we put in the two sets of data that we have, solve these two simultaneously, and we can get our latent heat of vaporization and our B constant. Okay, so now once we have this, we can go on to part B, which requires us to draw a diagram and to do a material balance problem. So we have air saturated with chlorobenzene at a particular temperature and pressure. It's cooled to some temperature and at constant pressure. So the pressure is still the same at 101.3 kilopascals. And that turns out to be all the information that's given to us. So this is all that's given to us. We have a vapor stream coming in at T1 and P1. We have the vapor stream that's cooled to 58.3 degrees C at the same pressure. And we have a liquid stream. We know that in this case, only chlorobenzene is condensable, so that stream is just pure chlorobenzene. We have no molar flows. We have no compositions in this case. So let's label everything. Remember that in this case, no basis was given, so we need to pick a basis. I'm going to pick a basis in stream 1, and that is going to be 100 moles of our feed going into the condenser. In this feed stream, we have chlorobenzene and air, so those are the mole fractions right there. In the vapor phase, in stream 2 coming out of the condenser, we also have air and chlorobenzene, so we have N2 and the respective mole fractions. In stream 3, because this is a single condensable component, it is pure chlorobenzene. We don't need to label the mole fractions. We just need to label the overall flow rate of chlorobenzene, overall amounts of chlorobenzene in that stream. And I just put it in parentheses, chlorobenzene, to remind myself that this is just a pure stream of chlorobenzene. Here are our unknowns. Let's go through the degree of freedom analysis. We have 6 different unknowns. We have 2 species, so we have air and chlorobenzene. We have 2 constraints. In stream 1 and stream 2, we have the sum of mole fractions equals to 1. So 6 minus 2 minus 2, we still need 2 more equations. And in this case, both our equations are Raoult's laws. We have Raoult's law for chlorobenzene in 1. This is going to be the unique one that I want to spend more time talking about, because all the question says is that stream 1 is saturated with chlorobenzene. So why can we use Raoult's law? Because when we are talking about a saturated stream, that means our chlorobenzene is right at the dew point. And when we talk about the vapor-liquid equilibrium, we have this saturated vapor that is in equilibrium with a liquid that is hypothetical. There's no liquid in this stream. But hypothetically, if you put in 1 more molecule of chlorobenzene, that molecule will condense right away into a liquid. So with that, we're going to have a degree of freedom of 0. Remember the Raoult's laws for streams 2 and 3, that is where we have vapor-liquid equilibrium in those 2 streams. All right, so let's start with solving the Raoult's law in stream 1. And here's our Raoult's law, writing the Raoult's law for stream 1 for chlorobenzene. Again, this term actually doesn't exist. This variable does not exist anywhere in our diagram because there is no liquid in stream 1. This is a hypothetical first liquid droplet that is in equilibrium with the saturated vapor. We are right at the dew point. Any more chlorobenzene and it will turn into a liquid droplet. Because this is a single condensable component, that hypothetical first liquid droplet is going to be pure chlorobenzene, just like we are condensing it in the output streams after the condenser. So that's going to be 1. And so now we have our equation that's simplified. How do we find the pure component vapor pressure at 130 degrees C? We have the Clausius-Clapeyron equation from part A where we have solved for our 2 unknowns. So now we just have to put in the temperature as 130 degrees C, use our latent heat of vaporization and constant B that we found, put it into the equation, and we can get our pure component vapor pressure of chlorobenzene at 130 degrees C. Put it into our Raoult's law, simplified Raoult's law equation, and making sure that the units are consistent here, we find the mole fraction of our chlorobenzene in our input as 0.963. All right, so from here, we can also use the constraint to find the other one. So our mole fraction of air, 0.037. All right, let's go on to our second Raoult's law, which is the Raoult's law for vapor-liquid equilibrium of chlorobenzene that's in the vapor in stream 2 and in the liquid in stream 3. So here's our Raoult's law for that. And again, because this is a single condensable component, our mole fraction of chlorobenzene in the liquid is just 1. It's just pure chlorobenzene there. From that, we see that we have a simplified Raoult's law and we can calculate our mole fraction. In this case, the P star at 58.3 turns out to be one of the temperatures given to us in the question, so we don't need to recalculate that. That was just 60 millimeters of mercury. All right, put all the numbers in and we have our mole fraction. use our constraint to find the other mole fraction. So once we have that, we have finished our constraints, we have finished our laws, write our two balances. That should give us our last two unknowns. The air balance, from here, the only unknown left is our N2, and we get N2 as 4.02. Do an overall balance, the only unknown left is our N3, and we solve for that. So the percentage of chlorobenzene that has condensed is the amount that came out in the liquid divided by how much you put in initially. How much you put in initially is Y in stream 1 times N1. And once you put in the numbers, put it in your calculator, and you see that you actually condensed 99.7% of the chlorobenzene. And so in this case, this is a way that you could separate out your chlorobenzene. If you have something like that of a system and you want to just get out your chlorobenzene, just put it through a condenser and you can do so. So that's all we have for this example. We are actually done with our material balance. So we're going to switch gears in our next lecture where we're going to start to talk about energy balances before we put it all back together again into our material balance. So work hard, be smart, and I'll see you in the next lecture.